to today's lecture, which will primarily be on chromonic liquid crystals and nanostructured liquid crystals in devices. It's a great pleasure. I'm Dr. Chakrabarti from Durham University. It's a great pleasure to have Professor Oleg Lavrentovich deliver this lecture. He needs no introduction. People who are interested in liquid crystals, I'm sure you've read the book by Professor Maurice Kleeman and Professor Lavrentovich. So, thank you very much.
Thank you. So I'll be talking about chromonics. This work was done primarily by the graduate students at the Liquid Crystal Institute and Chemical Physics Interdisciplinary Program at Kent. And you see the names Yunkiki, Chenhui, Peng, Shuangzhu. All of them are current students, and also all of them are participants of this camp. The most recent graduate was Hyung-Sik Park, who is now working for Samsung in Seoul. And Ivan Smaryuk did some of the pioneering research. Now he is associated, most less your boss here at IUCAM, but also professor at the University of Colorado. And this work, of course, would be possible with many collaborators that work with us. Sergei Shayanovsky at the LCI, Sam Sprung, Jim Gleason at Department of Physics in Kent, and Nazarenko and Nastashin in Ukraine, and Lana Protora, who is now at the Crystal Diagnostics company that, by the way, develops products based on chromonic liquid crystals. So this is the outline of the talk, but I would rather just go directly to the presentation and start the discussion with the observation that liquid crystals are not only of the type that you might find in the display panels when you have 100% of space occupied with the molecules that are organic and elongated and try to pack parallel to each other because they are basically touching each other and prefer to occupy the volume being parallel. Many years ago, in works by Bragg, by the way, done here, people observed that in water solutions of some elongated objects, you also might find orientationally ordered structures. And this is the photograph of the tobacco mosaic virus that inspired, not exactly this photograph, but a similar one, that inspired Onsager to consider a question whether the nematic type of ordering can occur in dispersions of long, thin rods dispersed in water. And his argument that it might happen was as following. So consider that you have a dispersion and the concentration is small. So the rods will be distributed randomly to maximize the entropy of translational motion. But then if you increase the concentration of the rods, you would observe that this tendency to distribute themselves randomly would be hindered by the fact that they might stuck into their neighbors and they would not be allowed to move freely, as for example shown for this red rod. And the solution for such frustration, Onsager saw in a simple trick. Let the molecule realign parallel to each other. In this case, these static hindrances kind of disappear because now you see that the red particle or molecule can move in the direction up and down and probably even to the side if it waits for the neighbor to move itself. And so this was the idea behind the beautiful theory that he developed that just compares two different contributions to the entropy, one associated with the positional, translational displacement of the particles, and another one considering the alignment of these particles with respect to each other. And he demonstrated that at some critical concentration or volume fraction that depends on the ratio of the length to the diameter of the particles, you would have a transition from the isotropic ordering here at low concentration to the nematic ordering at high concentration. By the way, a very similar argument can be applied to the transition from the nematic phase to the smectic A phase. So we will be talking about systems that are somewhat different from the on-Sagar model. In the Sagar model, it's just a rod that is long and thin. In our case, this rod doesn't have a fixed length. The rod is formed temporarily, if you wish, by disc-like molecules that, when thrown in water, are trying to behave in such a way that do not allow water to go into their hydrophobic phases. So what they do, they stack on top of each other, hide in their faces, and then expose these ionic, in this case, or just polar groups, in the case of some other molecules, on the periphery. So you have an interface between the organic material inside, the aggregate, and water outside that is formed by non-covalent bonding of the molecules. So here you see two typical examples that are most well-known chromonics. Disodium chromoglycate, it's interesting that this material in its pure form without any additives is used as a medication. People with asthma take it to relieve the symptoms of asthma. Sunset yellow, if you drink a lot of Mountain Dew, for example, you might have a lot of this material inside your body, or a similar one, because it's a colorant that is more or less harmless, and it also forms the chromonic aggregates when you throw it in water. The picture on the top shows you numerical simulations of what happens if you include the non-covalent bonding between the disc-like molecules in some solvent. You see here that these molecules try to form columns, and the columns are more or less flexible, and they are of variable length, and this was done at the University of Colorado in laser group. The materials of this type are known for already more than 100 years. There were observations of birefringence in the solutions of disc-like molecules that apparently form, or as we know now, definitely form the columns. They commonly occur in molecules that have extended polar aromatic core and ionic groups at the periphery. And if you think about this feature, then you will realize that you can easily find them in dyes, because dyes are typically represented by molecules with polar aromatic core of more or less extended dimension. It is interesting that you can see a parallel between the chromonic type of ordering and structure of DNA. Here on the right, I showed the pictures from the science publication by Noah Clark and Tommaso Bellini group, in which the small oligomers of DNA are shown to stack on top of each other, forming nothing else but chromonic aggregates. And the only difference here is that instead of really coin-like individual units, as in the example with sunset yellow, for example, you have short cylinders that are packed in the same manner on top of each other. And so with this, I would like to try to explain you why the term chromonic was invented. It was invented by John Lydon. It didn't exist before. He was one of the pioneers in the field, and he thought that the materials are kind of so unique in their properties that there should be some special name for them. And he was thinking that disodium chromoglycate, which is spelled, by the way, differently than chromonic, is one of the well-known examples, so it might, the term might include something from disodium chromoglycate. Then he thought of chromosomes. You know, the chromosomes, who knows why the chromosomes are called chromosomes? Raise your hand. Why the things that are, you know, genetic information bank are called chromosomes?
Because you have some color maybe, somewhere?
Somewhere, exactly. So many years ago, like 120, people started to use microscopes to see the biological cells. And by accident, they found that if you stain the cell with some dye, then you have a very strong contrast between some pieces of the cell and others. And they saw, tiny elongated things that would be especially easy to color with the dye. And they called them chromosomes, just because of that. They didn't know what they are. But the point was that if you see this Noel Clarke's picture and the DNA, you can easily imagine that there is a space for the flat disc-like dye molecules to intercalate between the units of DNA or the base pairs of DNA, and that way show the color when you stain them. So, and Lydon thought that chromosomes and chromoline should be combined in the term that he said, let it be chromonic, and this is what we have right now. So here you see the typical textures of the chromonics in one of the material, chromoline in this case. You might see that besides the isotopic phase, we have C, which denotes the columnar phase, and N, which denotes the nematic phase. And we will be dealing mostly with this nematic phase, and it's surrounding the biphasic region in which you have coexisting nematic and isotopic phase. So what's in the math? You might have noticed that I use an abbreviation LC squared for these materials. Of course, it's it's a lyotropic chromonically crystals, but it also has some connotation with the properties of this material. So if you compare them to the Onsager model and then to the regular Lake crystal, you would see a difference in two respects. In the case of Onsager, you're dealing with a system that is not sensitive to temperature. All you need to cause a transition from the isotropic phase to the nematic phase is to change the concentration of the dispersed material. And if you remember that everything is based on entropy, the two entropy terms, orientational and positional, have the same scaling with temperature. So it's not going to have temperature dependence. Now, in the normal liquid crystal like 5Cb, the material that we use in displays, the situation is different. The concentration is already kind of 100%, so you cannot change that much. The only thing that you can change is temperature, and as we know well, if you change the temperature, then the material melts into the isotopic phase. So the chromonics are double liquid crystals, if you wish. You can change their phase state either by temperature or by the concentration, and it's clearly seen in this phase diagram, because on the x-axis I have the concentration of the material, and on the y-axis I have the temperature, and the boundaries of the phase are tilted. That means that you can go from the nematic phase to the isotopic phase either by increasing the temperature or by decreasing the concentration.
Oleg.
Yes?
Is there anything special about that point where three lines phase transition meet?
Yes, but I'm not going to talk about it. So the question is, if you have such a huge sensitivity of these materials to all these parameters, what would you expect from the point of view of their elastic properties, viscoelastic properties, surface properties, electro-optics, and other things? So it appears that these properties might depend strongly on both temperature and concentration. But then you think, but why should I care? And for a while, these materials were not that known in the community, simply because no one knew what are they good for. And if you don't know what are the materials good for, then there is little incentive to study them. And so our first work was in fact to find whether there is something that we might find practical with these materials. By the way, I mentioned that disodium chromoglycate is used as an anti-asthmatic drug, but there is no work that would connect its mesomorphic properties to therapeutic ability. And so that piece of work is still kind of not clarified whether there is any link between the mesomorphism of disodium chromoglycate and its useful properties. So we started with a couple of ideas. One of them was that if you look at the chromonic materials, you might notice that they are water-based, and that is good if you would like to interface the liquid crystal with biological things. On the other hand, they are not surfactants, typical surfactants, these molecules with a polar head and then a flexible tail. Surfactants are good for scientists doing fundamental research and applications such as cosmetic industry. But they're not good for many biological cells because surfactants have this nasty ability to rupture the membrane of the biological cells, and many cells simply die when you put them in contact with surfactants. This is why we are using soaps, and people use surfactants in hospitals to disinfect the environment. So in our case, the molecules are totally not surfactant. They don't have these aliphatic tails. You cannot say that they have some polar head. So it's just a flat molecule with practically no flexible part. So it turns out that it's very friendly to biological systems. It doesn't kill the biological cells when you throw them in the environment. So we thought that one of the applications, and I will talk about just this application in a moment, might be the biosensing application. Then we realized that the materials might be good to prepare well-aligned arrays of organic molecules, such as shown here in their semi-dry form. Here you see the almost monomolecular layer of chromonic molecules that preserves the nematic water, despite the fact that water is gone, more or less completely. This is the atomic force microscopy image, and these films show very interesting semiconducting properties. So it's an example of organic semiconductor. Then you can use the ordered structure of chromonics to align other materials, such as carbon nanotubes. This is the work that started by Ivan many years ago, in fact, and only this year we saw it published because there were many interesting features that required additional work. Then we found that golden nanorods or metallic nanorods can be assembled in different fashions by small aggregates of the chromonic molecules. Here you see that just by slightly changing the chemistry of the solution, you can direct the gold nanorods to assemble parallel to each other, forming rafts like this, or forming chains, like shown on the right-hand side. And in both cases, the glue material is the chromonic aggregate. We think that the assembly proceeds through the electrostatic interactions, and we consider the aggregate as a kind of polyion that has charge larger than 1, because the groups and the periphery of the chromonic aggregate are dissociated. So I'm not going to describe all these applications, just one of them, because it's based on very simple physics that can be presented to you here, and I'd like to present this next two slides because they explain many things in the liquid crystal. So for those of you who saw them probably 3 or 4 times, I apologize. But for the rest of you, I'd like to say that there are 2 important things to remember about any liquid crystal. First, that it has surface anchoring, which is the anisotropic part of the surface tension. What it means is that if you have a substrate and you put a liquid crystal, then there is always some preferred orientation of the director at this surface. And to change that orientation, you need to spend some energy, to spend some work. And of course, the larger is the surface, the bigger would be the amount of work, and you can write it as some coefficient. It depends on anisotropic interactions of molecules at the interface and the surface area, L squared. Now, the liquid crystals are also elastic media. That means that if I want to change the orientation of the director that is normally uniform in space to something that is splayed, like my fingers, I need again to spend some work, and as you know by now, this work is proportional to the density is proportional to the elastic constant called the Frank constant multiplied by the divergence of n or curl of n or some other combination squared. And that gives you an estimate per unit volume that this energy of elastic distortion should be k over r squared. Now if you integrate it over the entire volume, which is r cubed, then you would realize that the estimate for the elastic energy is something that looks like KL. L is the size of the system. And it's very interesting. If you compare the surface anchoring and elastic energy, you would see that the surface energy grows faster with the size of the system than the energy of elastic distortions. And then you can kind of guess what would happen if you have a colloidal particle inside a Lake crystal. So what it should be is that the colloidal particle also has some surface anchoring. Let's suppose that it's normal to the boundary. And if you put the particle in the uniform nematic, then you would expect two things to happen. The particle would like to set the normal orientation, and that means radial distribution of the director. But it would cost some elastic energy. So what happens would depend on the balance of these two tendencies. If the particle is small, and small meaning smaller than elastic constant k divided by W, if you consider these two terms, then as you see from this plot, the linear elastic energy is much more important than the anchoring energy. And so that means that the director will be uniform around the particle, and the surface anchoring conditions will not be satisfied. But now if the particle is big, like the one shown here, larger than k over W, then you would see director distortions around the particle. They would serve to kind of provide a transition from the normal boundary conditions that are now satisfied at the surface of the particle and the uniform director field outside. So from here you see that you would expect very tiny particles smaller than k over W. And by the way, what is the typical value of k over W in Lake crystals? Who knows? Raise your hands. This quantity, k over W, has the dimension of length. So what is your guess about the value of it?
1 to 10 micrometers.
Why is that? Is there any typical size in the Lake crystal that corresponds to 1 to 10 micrometers? How does it compare with the molecular impact?
It's like 100 times.
How is it possible? We are used to think that in many physical systems, you should have the internal length, and then this length would show up in all these physical quantities like one elastic constant divided by another. Exactly. So this is to some extent a question that in nematic Lake crystal, the only length that you obviously see is the length of the molecule, and this is just a few nanometers. But when you construct this length scale k over W, it turns out to be much larger than the molecular scale, and it's a remaining question in the theory of Lake crystals that Michael Osipov was making a presentation about a couple of months ago at the Institute. That it's not quite clear how might it happen that the surface properties of Lake crystals are so interesting that they produce this. You're exactly right. Extrapolation length of anchoring in the range of micrometers in many occasions, which is much larger than the molecular scale. So there is a lot of stuff to still learn about Lake crystals, even at this fundamental level. So, but now, if we kind of expect that small particles do nothing to the Lake crystal and big particles distort, and the distortions are easy to visualize because that's what we do when we look at our computer screen, then we can propose the idea of bacterial detection. So you know that in nature, in our bodies, the bacteria are detected by the antibodies that are looking for the specific molecular markers at the surface of bacteria. And when they find something of interest to them, they bind to it, and since antibodies have two linking groups, what happens is that eventually they create an aggregate, a so-called immune aggregate. And so we thought that if this is the case, it's like having little tennis balls assembled into the big soccer ball, and now you can see the soccer ball because the director is distorted around this immune complex. And in fact, this is just the illustration of how the E. coli is being assembled into the immune complexes, and this is the experimental verification of the idea. If we have bacteria that are individually dispersed in the Lie crystal, we see no light transmission through this cell because the bacteria do not disturb the uniform director. But once the antibodies get into the play and assemble these huge soccer balls, the director starts to be distorted around the complexes, and between cross-polarizers you can see a leakage of light, and that immediately tells you that there is a presence of the harmful bacteria. So now you kind of know that the materials might be of some potential interest. Of course, there is a huge and difficult road between this simple idea and the real sensor that can be commercially produced. But still, you are now motivated to do something about the properties of these materials, and I will talk about the elasticity first. So, to measure the elastic constants of Lie crystals, you need to exert some external torque that wants to realign the Lie crystal, and then to see how the material responds to this external torque. And typically, it's done with magnetic field or electric field. In our case, magnetic field is much easier because electric case involves motion of ions, and that complicates things. So the simplest experiment is the one in which you have a homotropic cell, so that you have two plates and the molecules are perpendicular to them, and then you apply the magnetic field parallel to the director. If you remember the structure of the chromonics with polar aromatic cores being perpendicular to the columnar axis, you would guess that the anisotropy of diamagnetic susceptibility is negative, and that is correct. So if you apply the magnetic field in this direction, the director would tilt, and that would happen when the magnetic torque overcomes the stabilizing torque of surface anchoring and elasticity. And this simple expression, I don't see it here, which is that the critical value of the threshold is proportional to elastic constant divided by delta chi, and I think I should put something like pi over d as the coefficient here, allows you to determine the elastic constant in this case of band deformation, because as you might see, the original deformation is of the band type. And if in addition to that you measure also the delta chi, which the student that performed this work, Schwang, did, you would obtain the absolute value of the elastic constant, and they are shown here. Now, who can tell me what would be the normal expectation for the value of the elastic constant in a nematic Lie crystal? What would be the guesstimate? What would you expect? I show that it's about, from 1 piconewton to 10 piconewtons. Why is that? So if you read Dejean's book, you would find a very simple explanation of the range of values of the elastic constants in normal Lie crystals such as 5Cb. So Dejean said, look, the nematics melt into isotropic phase at temperatures that are not that far from the room temperature, right? 5Cb, for example, melts at around 37, 36, depending on the purity. So, and there is this length of molecules in the Lie crystals. So he said that since K has the dimensionality of a force, then the estimate would be the energy responsible for nematic ordering divided by some length, and there is no other length but the length of the molecules, because we are talking about bulk properties, not about the surface properties. And then he said, okay, if I recall that pneumatics melt at the room temperature or so, then the estimate for this energy that is set in orientational order would be Boltzmann constant multiplied by something like 300 Kelvin, and then divided by 1 nanometer. And then you would get 4 piconewtons as the potential estimate of the elastic constant. And it's amazing that in Chromonics you have a very similar order of magnitude for these quantities. So what is interesting is that the Lake crystal, of course, shows at least three different, we are not talking about things like K24 and K13 here. We are talking just about 3 bulk elastic constants. They're all different. Again, if you look at the values that were obtained in different geometries of the Fredericks transition, you would see that K1 is a little bit smaller than K3, and both of them are much larger than the twist constant K2, which is smaller than the 1 piconewton. So if you plot the temperature dependencies of the ratios of the elastic constants of splay K1 to band, you would see that it goes down, which is rather unexpected because it's just the opposite what you would observe for practically any other thermotropic material. So apparently in the system in which the building units are not a given constant, in which the building units are aggregates that can be elongated when the temperature drops or shortened when the temperature rises, the elasticity has something to do with this self-assembly of the aggregate. And if you look at the literature of theories that consider elasticity of various dispersions in solvents, you will find that people associate the band constant, which is deformation shown roughly here, with the so-called persistent length of the aggregates or molecules or polymer chains. And it makes sense. If the aggregates are very long or very short, it doesn't matter. What matters is that how easy it is to bend each concrete molecule into this configuration shown over there. And the models would predict that the elastic constants of band are proportional to the persistent length, which tells you how rigid is the molecule with respect to the band deformations. In polymers, for example, if you have a very, very long molecule, the persistent lengths matter the distance over which you lose correlation between the orientation of this part of the molecule and the orientation of this part of the molecule. So this is one observation. Another observation was made by Bob Mayer, who said, look, K1 should not depend on the persistent length. What it should depend on is the contour, the entire length from one end to another end of the molecule. And it doesn't matter much whether the molecule itself is wobbly and flexible. What matters is just the distance between the two ends, because if you would like to create splay deformations like I show with my fingers, to fill these empty pockets of space with the material, which you should, you need to find an end of another molecule to stick it here. And so he reasoned that if the molecules are very long, then it's very hard to find all these ends to fill into the pockets. And that means that the elastic constant of splay will be proportional to the length of the molecule. The longer the molecule, the harder it is to splay. And so we played with this idea, which is very simple, that the ratio of K1 over K3 should be the ratio of two lengths of the chromonic aggregates, and then we considered what might be the value of the average length of the aggregates, and the simple model suggests that it should be a very, very strong function of temperature and concentration. Here again, it's the balance of entropy that would like the monomers, the little chromonic molecules, to be dispersed in space freely, and the sticking energy, this non-covalent bonding, that hydrophobic bonding, if you wish, that keeps them facing each other within the columns, that sets the length or the aggregation number in the system. So you might see that by just balancing the sticking energy and entropy, you come up with the average length of the aggregates that is proportional exponentially to 1 over temperature. And a similar expression for the nematic phase. I'm just going to talk about this. So by taking this into account, you now find a quite reasonable explanation of the elasticity of liquid crystals of chromonic type and their basic dependence on the concentration, which is shown here as the volume fraction. Of course, much more should be done. We are working now, Schwang and Chen-Hui, on how these elastic constants depend on ionic content of the dispersion. But the first results are kind of encouraging because, for example, what you find from the temperature dependence of the elastic constants is that you can estimate the sticking energy. It turns out that it's about 10 Boltzmann energies, which is much less than the covalent bonding, but is a little bit higher than, let's say, the energy of hydrogen bond. So, and finally, I would like to discuss tactoid. So this is the region that is relevant to your question, but not that complicated. It's just the biphasic region. So when you are finding yourself in the domain in which the nematic and the isotropic phase coexist. So when they do, then you have the islands of the nematic or the isotropic phase being embedded into the opposite phase, and the structure is sometimes more or less round, sometimes is not round. It is determined by the balance of anisotropic surface forces and elasticity. And the first observers, among them Zucker, who saw the coexisting of the nematic and isotropic phases in similar systems, called them tactoids. And here is the picture from Bernal's article in which he demonstrated how the molecules are supposed to arrange themselves within these germs or within these islands of the nematic phase. And so we did the experiment in which we just wanted to see how the tactoids would look in the chromonic liquid crystal, and we saw beautiful pictures. You see the lemon-like tactoids here. Then in the vicinity of the triple point, you see more interesting structures such as toroidal droplets of the condensed phase, and it is schematically shown here. But then we look by taking our three-dimensional microscope. Again, Ivan Slavik has a lot to do about this microscope that allows you to observe not only the in-plane structures but also the vertical cross-sections. And what you see is that the tactoids, these black regions, are not in the bulk as we are used to think most of the time. They represent droplets that are sitting on the top or bottom of the cell, being attached to the substrate. So it's something like this, and nothing in common with this axisymmetric structure. And then the second interesting thing was that if you look at this tactoid, you see that they are chiral, and it's very easy to check by decrossing the polarizers. If you decross the polarizers this way and this way, you would see two different textures. And why are they chiral? There is nothing chiral from the molecular point of view in the structure. The reason is very simple. Again, you have an interplay of elastic properties and confinement. In this case, what you need is just the fact that the elastic constant K22 is very small. So if you have a wedge-like geometry that forces the director to be tangential to the two plates and thus splay, this splay deformation costs a lot of energy, and it can be reduced if instead of splay you have a twist of the director. If the director can twist around and be parallel to the normal to the screen, I eliminate the deformation completely. And that explains the structure of these twisted tactoids. I'm not going to discuss it in any detail because the message is very clear. You have anisotropic elastic properties, you have the confinement imposed deformations, and the system adjusts to these confinement with non-trivial boundary by selecting the deformations that are of the smaller energy density. And finally, the interesting thing is that you probably heard about these analogies between liquid crystals and defects and cosmology. So many years ago, Hubble proposed a mechanism by which you can explain formation of cosmic strings. They are nothing else but disclinations that form when two bubbles of new phase collide in the universe, and there is a chance that they collide in such a way that they form a disconnection. And you can stage the very same thing with the Chromonic. Here I just show you how you nucleate the islands of the nematic phase, and when they collide and when they have different orientation prior to the collision, you see the formation of disconnetions here. So the configurations might be very complex, so to describe them you need more or less generalized approach that doesn't care about little details, but gives you the number of potential defects as the function of how many cusps that you have at the surface of this tectoid you have, and things like that. So I'm not going to tell you about all the details here, but an experiment like this poses a very interesting question. Suppose you have this tectoid, and inside of the tectoid you have a defect, or you have the other thing, like the formation of the isotropic phase at the core of the topological defect. In that case, your tectoid doesn't look at all like the spindle. It looks like this triangular thing with curvy edges, or you might find some other interesting things. So you're dealing now with the problem that an elastic body would like to minimize both the elastic energy inside and the interfacial energy at the boundary, and this problem doesn't have a solution even for the two-dimensional case. And the only thing that you can do at this stage is to assume that, for example, the director is frozen, and then you can minimize the interfacial energy of the inclusion, taking into account that the surface tension is anisotropic. And here are the predicted shapes of the nematic islands in the isotropic fluid as a function of the surface anchoring anisotropy. So the higher is anisotropy, the more kind of cuspy the interface becomes, and this is the same for the problem. So I would like to finish with saying that LC squared are very interesting. You have two axes to control them, temperature and concentration. You can measure the elastic constant that show huge anisotropy when you compare twist to splay and bend. That leads to interesting things such as chiral symmetry breaking in a situation when there are no chiral molecular species. And you can explore the nucleation of the nematic phase from the point of view of generation of topological defects and their collective behavior in the system. Thank you very much for your attention.
Okay, so are there any questions?
Yeah, you've shown that you could align a chromonic in a magnetic field, and you can also do it, I guess, by rubbing. You should also try electric fields to align these kinds of molecules.
Yeah, it's an important and very difficult question. You see, the Lyotropic liquid crystals are extremely hard to align, and this is the illustration of why it's so. Because again, when the aggregates are kind of long, the entropy is coming into play. Because again, to have, for example, a homotropic alignment, you need to find enough ends of the aggregates to organize this alignment. So we spend a lot of time. The short answer is that you can still find the materials that would provoke the homotropic. Plenary is relatively easy, you just use polymers and rub them. But the homotropic is really difficult. But again, if you think about what type of materials you can use, for example, materials with kind of polyaromatic structure as the aligning substrate, then you can achieve both planar and homotropic alignment. It's better not to involve the magnetic field, or electric field, because that will be used to realign the director.
Okay, so electric field never didn't work.
It kind of works in very special cases, but you know, it's not a general technique that we are using. Just the substrates coated with the proper surface alignment layer are the way of choice, the alignment of choice.
I had some questions about Hongshik's work on the nanoparticle concatenation. And so if I understand the mechanism right, there's a depleted region around the edge of the nanorod that allows the chromonic to go to the ends. It's concatenated neuron. So is there anything special about the chromonic, or would any molecule with an affinity particle go there? And could you use that as your biosensing mechanism?
Yeah, it might be probably, but you know, first answer is we don't know much about these things. The second is gas is that it's not so much excluded volume; it's electrostatic interactions mostly. You know, DNA is being a charged entity with 6 electronic charges per each nanometer of its length. And despite of that, it is tightly packed in you know, viruses, for example, or any other chromatin. So why is that? People believe because of electrostatic interaction, the ions of multivalency, like you know, spermine with 4 charges, they have opposite charge to the charge of the surface of DNA, and they kind of attract the 2 DNA strands together by providing this colonic attraction. And we think that chromonic aggregates are similar to multivalent entities that electrostatically allow 2 similarly charged gold particles to come close to each other and be linked by the opposite charge of the chromonic aggregate.
You haven't tried like diphiles or anything like that?
No, what we did here to switch from one behavior to another is that the functionalization of the gold particles is different. In one case, you have the sides that are more electrically negative, and in another case, you have the top and bottom that is more electrically negative, and that directs the chromonic aggregates to either the top and bottom or to the sides, and that's how the change in geometry occurs.
And could you control the degree of concatenation? I mean, you know, 10 rod, you know. something.
Well, that is harder. We had it with the pH. If you change the pH, what happens? The chromonic aggregates disintegrate or assemble again. And by controlling pH, we were able to control the aggregation number of the gold numbers.
Okay, I guess we are running short of time. Let's thank the speaker for a lovely talk.